Back in the day, a machine was just a machine. It did whatever machine things it did, like stamping metal or turning a propeller, or maybe washing your clothes with a fair amount of help on your part. But nowadays, machines have to do more than just their given mechanical function. Now, a washing machine is supposed to be smart. It's supposed to learn about you and how you like your clothes, and it's supposed to adjust its functions according to its sensors, and it's supposed to send you a gentle message on your phone when it's all done taking care of everything. This is a big change, not just for washing machines, but for so many other machines and for data science processes as well. This gets to the issue of machine learning. And a very simple definition of that is the ability of algorithms to learn from data and to learn in such a way that they can improve their function in the future. Now, learning is a pretty universal thing. Here's how humans learn. Humans, memorization is hard. I know this. I teach, and memorization is something my students struggle with every semester. On the other hand, spotting patterns is often pretty easy for humans, as is reacting well and adaptively to new situations that resemble the old ones in many but not all ways. On the other hand, the way that machines learn is a little bit different. Unlike humans, memorization is really easy for machines. You can give them a million digits, it'll remember it perfectly and give it right back to you. But for a machine, for an algorithm, spotting patterns in terms of here's a visual pattern, here's a pattern over time, those are much harder for algorithms. And new situations can be very challenging for algorithms to take what they learned previously and adapt it to something that may differ in a few significant ways. But the general idea is that once you figure out how machines learn and the ways that you can work with that, you can do some useful things. So for instance, there's the spam email, and you get a new email and the algorithm can tell whether it's a spam. I use a couple of different email providers, and I will tell you, some of them are much better at this than others. There's also image identification, for instance, telling whether this is a human face or whose face it is. Or there's the translation of languages, where you enter text either written or spoken, and it translates it back. A very complicated task for humans, but something that machines have learned how to do much better than they used to. Still not 100%, but getting closer all the time. Now, the important thing here is that you're not specifying all the criteria in each of these examples, and you're not laying out a giant collection of if this then that statements in a flowchart. That would be something called an expert system. Those were created several decades ago and have been found to have limited utility, and they're certainly not responsible for the modern developments of machine learning. Instead, a more common approach, it really is to just teach your machine. You train it. And the way you do that is you show the algorithm millions of labeled examples. If you're trying to teach it to identify photos of cats versus other animals, you give it millions of photos and you say, this is a cat, this is cat, this is not, this is not, this is. And then the algorithm finds its own distinctive features that are consistent across at least many of the examples of cats. Now, what's important here is that the features, the things in the pictures that the algorithm latches onto may not be relevant to humans. We look at things like the eyes and the whiskers and the nose and the ears. It might be looking at the curve on the outside of the cheek relevant to the height of one ear to another. It might be looking just at a small patch of lines around the nose. Those may not be the things that humans latch onto, and that sometimes they're not even visible to humans. It turns out that algorithms can find things that are very subtle, pixel by pixel changes in images, or very faint sounds in audio patches, or individual letters in text, and it can respond to those. That's both a blessing and a curse. It means that it can find things that humans don't, but it also can react in strange ways occasionally. But once you take all this training, you give your algorithm millions of labeled examples, and it starts classifying things. Well, then you want to use something like a neural network, which has been responsible for the major growth in machine learning and data science in the past 5 years or so. These diagrams here are different layouts of possible neural networks that go from the left to the right. Some of them circle around or they return back to where they were, but all of these are different ways of taking the information and processing it. Now, the theory of neural networks or artificial neural networks has existed for years. The theory is not new. What's different, however, is that computing power has recently caught up to the demands that the theory places. And in addition, the availability of labeled data, primarily thanks to social media, has recently caught up too. And so now we have this perfect combination. The theory has existed, but the computing power and the raw data that it needs have both arrived to make it possible to do these computations that in many ways resemble what goes on in the human brain and that allow it to think creatively about the data, find its own patterns, and label things. Now, I do want to say something about the relationship between data science and machine learning. Data science can definitely be done without machine learning. Any traditional classification task, logistic regression, decision tree, that's not usually machine learning, and it's very effective data science. Most predictive models, or even something like a sentiment analysis of social media text. On the other hand, machine learning without data science, well, not so much. It's possible to do machine learning without extensive domain expertise, so that's one element of data science. On the other hand, you would nearly always want to do this in collaboration with some sort of topical expert. Mostly, I like to think of machine learning as a subdiscipline of data science. And that just brings up one more thing I want to say. The neural networks, and the deep learning neural networks in particular, that have been responsible for nearly all of these amazing developments in machine learning are a little bit of a black box, which means it's hard to know exactly what the algorithm is looking at or how it's processing the data. And one result of that is it kind of limits your ability to interpret what's going on, even though the predictions and classifications can be amazingly accurate. I'll say more about neural networks and these issues elsewhere, but they highlight the trade-offs, the potential and the compromises that are inherent in some of these really exciting developments that have been taking place in one extraordinary influential part of the data science world.